Hello, this is Brian Kinghorn, and today I'm going to tell you about some extended applications in the new version of Multiple Enduses under MateSel. A couple of weeks ago we released a video on this new version of Multiple Enduses. It's got considerably increased functionality and much better operation within MateSel. However, we left some components for this later video, so the first video to look at is this previous one before moving on with the current one that you're looking at now. So this is a list of the applications we're going to look at today, and our experience is that after we release this new version, users will find other ways of using these things. And before we go on, a couple of points to make. One is that we're going to use the simple demonstration file that is released with MateSel, so you can probably follow along if you want to with these examples. And that's rather a small data set, so we're going to be dealing with unusually small examples. That gives for a quick illustration as well. And also, being a simulated data set, it's reasonably straightforward and well behaved. You might find that for some of these applications you get better results than indicated in this video. For example, if you're looking to set up sire and dam lines, it's quite possible that you've already secured some terminal genetic material and some maternal genetic material, and so you've already got that extra genetic variation in your population. As a starting point, I'll take a simple terminal end uses example with the nucleus supplying stock to itself but also disseminating to end uses 2 and 3. And there's a zero emphasis on coancestry in those two end uses, and there is a reduced emphasis on genetic gain for them in order that the nucleus is not compromised by the dissemination program. And here's the parameter file for this example. You can see that the index is the sole driver for end use 1. The first trait is the sole driver for end use 2, and the second trait is the sole driver for end use 3, and that's just so we can pick up on the results. Let's look at them quickly now. So we can see that the index is best in end use 1, the first trait is best in end use 2, and the second trait is best in end use 3, and that's exactly what we've asked for. And we can see that in the application. If we look at the matings that are actually made, we've gone here for 30 degrees, which means we've got some emphasis on coancestry in the first end use, and you can see some diversity in use of sires there, but there's no diversity management in end use 2 and end use 3 as you see down here. So what we can do now is move to some diversity management by changing the weighting for end use 3 to take account of the fact that there's some possibility of selection from that end use back into the nucleus, so that the progeny from these matings could end up being selected into the nucleus. So we invoke that by putting a weighting on coancestry for that third end use. Let's put a half on there. Save that, bring back the application, resume and update the matings as well. And you can see that for end use 3 there is now some variation in use. We brought in some other individuals to give some variation there, and these individuals will be lowly related to the rest of the population in end use 1. You can see that Connor is used in this end use, even though Connor is widely used in end use 2, but that doesn't matter because those matings are not going to give progeny that come back to the nucleus. However, we have to recognize that the extra diversity that is created in end use 3 is targeted at the whole population, not just end use 3. And it could be that our objective is to have some diversity in that terminal end use because we're not fully confident of the accuracy of the EBVs of the sires involved, and we don't want to put all our eggs in one basket. So that's a different situation that we can look at here. Some diversity in dissemination. So now we're going to assume that the progeny from matings in end use 3 do not have any chance of going back to the nucleus, and yet we are interested to have diversity in end use 3 for dissemination purposes. And the way that we do that is declare that end use 3 sits in a separate population. So when we manage diversity in end use 3, it's not going to relate to population 1. It won't be attempting to increase the genetic diversity in the whole of population 1 because it's just looking after itself in population 2. The way we do that is first of all to declare that end use 3 sits in population 2. I've changed the weighting for coancestry here from a half to 1, but in fact that makes no difference because these weightings are relative to each other within population. And that means that, for instance, if I change this 1 to a 10, it would make no difference because it says that all the emphasis is going to be on end use 1 within population 1. The other thing I've done is put some emphasis on managing genetic diversity in population 2. So now we've got 3 end uses but only 2 populations, and this is where we're declaring the management of coancestry at the population level, both within populations and coancestry between the populations. So here is the enduses.txt that reflects that. I've already made those changes. I'll save that, bring across the application, resume and update, which means it's going to take these values that I've made, and you can see there's some movement here for a change. So I haven't yet updated the matings, so that you can look and see the matings that we did have in Enduses 3, and then when I update them, we can see that there is some difference in the sires that are involved here. These are now concentrating solely on having extra genetic variation within Enduses 3. There's not much difference in this particular case, but in some examples it could be quite a different outcome. But of course you can have a mix of strategies, so that for some enduses where you're really confident that there are going to be no progeny from these matings to come back to the nucleus, it's fully terminal dissemination, then you can take the strategy we've just looked at. Whereas we can have a mixture, and for other enduses have some possibility of progeny out of these enduse matings coming back to the nucleus. And that's done here just by putting a weighting on coancestry for Enduses 2, which is still in population 1. However, that will still give diversity within Enduses 2, and so it is still a reasonable policy to use if you want diversity in your disseminated stock. Now with the lights on again, we can make a small modification to this example such that Enduses 3 is no longer fully terminal but is destined to be a new line. It sits within population 2. Now population 2, it is our intention that that will be a separate population with a different set of trait characteristics and independent diversity management. However, for a number of breeding cycles, we can implement this strategy in multiple enduses because it may take time to build up the size of population 2, and population 1 can continue to provide resources to build up that population. Now in this example, I will be pushing the genetic merit equally for population 2 as for population 1, and of course we'll manage coancestry in both of those populations starting off with equal weightings. Now you'll notice that parameters for committed matings have been added since the last video, and this is in reaction to a user in one of the intensive industries who is setting up a new line but didn't need committed matings for that new line because juveniles in the pipeline are not going to be candidates for that new line. So in this case we could put a weighting of 1 on population 1 so committed matings are properly taken into account, and a 0 for population 2 because this is a one-time creation of a new population. So these weightings are applied at the population level, but you'll read in the manual that we've already handled the impact of different enduse weightings within population as far as the impact on committed matings. What I'm going to do now is get rid of the Enduses 2 just to make it simple, and here we have just the 2 enduse example, 1 enduse per population. And parameters in enduses.txt are here, and here is the run that I've made. So if we look at the results and out enduses.txt, we can see the coancestries for the 2 populations, 0.1 and 0.06. One thing to point out here is that the coancestry between the populations is much lower, but that's because we generally don't have the self relationships in there. These figures are quite high for the population coancestries because the population sizes are small and the self relationships have quite an impact. So the coancestry between the populations is more or less equal to the inbreeding coefficient that you get on average within each population. Now you might be concerned that the coancestry is a lot higher in one of those populations than the other. Let's have a look at the results here and we can see why that is. You'll see that there's relatively little variation in sire use within Enduses 1, whereas there's quite a bit of variation in sire use within Enduses 2. And for this data set, that will be because there's more opportunity to access genetic merit in Enduses 1, such that Enduses 2 is carrying the can for diversity. We're still managing diversity across the whole run using the tools that are available in MateSel. So if you want to alter these figures that you've got for the coancestry within each of the populations, then you have to make alterations in enduses.txt. So let me do that now by pushing harder for low coancestry in that first population, and we'll go for less emphasis on coancestry in the second population. So save that, resume and update, and now we can hit print matings, and you can see that there's more variation in sire use in Enduses 1 and less variation in sire use in Enduses 2. And if we look at the results in enduses.txt, this is what we had before, and we can see that we've actually reduced the coancestry in Enduses 1 to a figure that's lower than it is for the second population. So then we would go back and make alterations to the weightings to make the outcome that we want for these two populations. We only need to make a small modification to this example to show the special case of sire and dam lines. So end use 2 is now the dam line, and that's targeting a population where the animals are good in maternal characteristics and they're to be crossed with animals from population 1 which are good for sire characteristics such as carcass value. So we've already got those covered in new line development, but the difference here is that we're going to cross these populations in order to get commercial product. So if we make these populations more genetically distinct from each other, then we will have reduced issues with inbreeding. And also there is the possibility that you could be targeting increased heterosis. You're not going to get much of that coming out of a single population. However, you can use genomic tools to help that, and you may already have resources within that single population which represent those two population types. So in order to make the populations more distinct from each other, we're looking for diversity between the populations. And these weightings down here are high for diversity. So if we want to have low coancestry, we want to have high weightings here. So I found a weighting of 1.75 gives a good sweet spot example where we're pushing to make these two populations more genetically distinct from each other. And this is just the same as we had before. You might recognize these coancestry figures down here. What we're interested in is the coancestry between the two populations. So let's make that alteration, 1.75. So we save that, resume and update, and come back and look at the results. So here we had a coancestry of 0.0366 between the two populations. That's now been reduced a fair bit without too much impact on the two populations. And that is directly related to the average inbreeding you were going to get when we cross those two populations. But I would be very careful about thinking you're going to get increased heterosis unless you've got the resources and tools to achieve that. If you do have those, then MateSel, I think, will be able to help you to target that outcome. So again, we only have to make a small modification to turn this scenario into the information nucleus or genomic reference population scenario. In the case of sire and dam lines, we were trying to pull the populations apart to make them more genetically distinct. Whereas with an information nucleus, we're trying to make it well related to the main population so that it's more relevant for generating genomic EBVs in that main population. So with sire and dam lines, we were trying to make them more distinct and put a large weighting here for that. So with the information nucleus, we do exactly the opposite. We put a small weighting in there in order to make the populations more similar to each other with high coancestry between them. Otherwise, the scenario is somewhat similar. But let's look at the parameters that we are using here. Well, first of all, I've biased the number of matings much more towards the main population, and these numbers of course are ridiculously small for real applications. They just serve for illustration. However, in real applications, if you've got large numbers of animals in the populations, then you can take the strategies shown in the video on genomic relationship matrix to handle large groups of individuals as if they were single animals or plants, and that can be handled quite quickly in MateSel. The next thing is that I've put the index as being the target trait for both the information nucleus and the main nucleus, although that isn't necessarily the case. But what I have done is put a much smaller weighting on the importance of genetic merit in the information nucleus. And that's because we want to have good variety in there to help make the calibrations. Of course, there are different ideas on those things, so you can choose your own parameters accordingly. And we've started off with no manipulation of the coancestry between the populations. And here's the result here. If we look at out enduses.txt, as before, the coancestries within populations are inflated by the self relationships because we have relatively small populations, and the coancestry between the populations is more or less equal to the progeny inbreeding. In this case it's a bit higher, probably because we're looking for coancestry within each of these populations. But the objective is to increase this coancestry between the two populations, the genomic information nucleus and the main population. So we go to enduses.txt and I'll put a -1 in there. Save that. Resume and update. And after about 5 seconds I can click print matings and come back to out enduses.txt, and this is the number we're looking at here, and that's gone up quite considerably. So you'll see that it is considerably more than the progeny inbreeding that you get with each of the populations, and that's because we've targeted a strong relationship between the populations. You may not be happy with those results. You may want to have greater genetic diversity in your information nucleus to give you better calibration potentially, but that's up to you. It's a question of discovering the weightings that give you the outcome that you want, as with everything else. So the last application I want to look at for use of multiple end uses is experimental treatments, or possibly some kind of special projects out of your breeding program. In this case, population 2 and population 3 are two experimental treatments, and if we apply multiple end uses here, you get mating recommendations. And that's appropriate if you're wanting to set this up to make matings to generate progeny that are going to be used for your experimental purposes. However, if you want to use multiple end uses to make selections directly into experiments, then there's a section in the manual that will help you to do that. Now, the great value of this is going to be in the trait distributions. We're managing the nucleus as normal with the index, that's in end use 1, and end uses 2 and 3 for the experimental treatments are going upwards for EBV in back fat and downwards for EBV in back fat. And that might be an example where you're setting up resources for a nutrition experiment or something like that. We're going to put less emphasis on the experimental treatments than on the nucleus, so the nucleus isn't compromised. Of course, we have 3 populations, and the co-ancestry management might tend to go something like this. We're going to use negative weightings on the diagonals to give low variation within treatments, and a negative weighting in the off-diagonal between them to give similarity between those two treatments, so that the animals in each of the two treatments are genetically more related to each other to give a fairer comparison. So let's look at the parameter file. Here you can see that I've given many more matings to the nucleus than to the experimental treatments, as you might expect, although the numbers overall are rather small, as we've discussed before. Here are our weightings for back fat, up and down. Let's have a look at the results for that in outenduses.txt. So for back fat, we've got a great increase and decrease in end uses 2 and 3 respectively. And when we look at the results in the application, we can see that Connor with the highest EBV for back fat and Sean with the lowest EBV for back fat are the two sires that are used unexpectedly there. So let's look at what happened in the results. We can see that the coancestry is really high for end uses 2 and 3, and that's because they're very small populations, and because of the way that coancestry is calculated, they are inevitably rather high. However, the off-diagonals are low and roughly equal to what the progeny inbreeding values are as expected. So what we want to do is increase this value to make the two experimental treatments more similar to each other. So let's go to enduses.txt. I'll put in a weighting of minus 0.4 in there. Save that. Resume and update. So that seems to have converged reasonably well. Let's update now on the matings. And we can see that we're using one sire across both the experimental treatments. That's the strongest way of making these treatments look like each other, to be genetically connected, is to use the same sire across both of them. So that will have quite bad consequences for our trait separation. Let's look at the result for that. And we can see we've still got some separation, but it's reduced probably too much. On the other hand, we've had quite a good increase in the degree of similarity between the two populations. The coancestry within each population has gone up a bit, but of course that's biased upwards for this comparison by the self-relationships within those populations, which you don't get here in the same way. And the cross-population increase in coancestry is quite substantial. But what we want is probably something in between. So let me try a much smaller weighting of 0.075. And I think that's going to give me a situation where I'll have different sires selected into the two experimental treatments. So I'll resume and update and come back to you once it's converged. So that's well converged, and now when we look at end uses 2 and 3, we have different sires that are being used. And the similarity that we're going to get between these two experimental treatments is going to be largely down to the female selections. So let's look at the end uses results. You can see that that coancestry is a good bit higher than it was. It's still rather different from the 0.2 or so that we had before, and that's largely because we're hopping between using one sire across two treatments and having one sire within each treatment. But the benefit of that is that we've now got good separation in back fat again, so that we have the experimental outcome that we may want of a good experimental contrast with an improved comparability between the treatments. Of course, now we don't have random selection of animals into experimental treatments, so you have to account for that in your statistical analysis, but we have managed to get a little bit more power. But as I said before, the main value of multiple end uses here is going to be in the trait distributions. But for your situation with a bigger data set and a richer data set, you may be able to get improved outcomes in terms of coancestry and comparability across treatments, as well as good experimental contrast for trait differences. That's us coming to the end of these two videos on extended features and multiple end uses within MateSel. We'll be releasing this as of version 16 of the MateSel Engine. So you'll appreciate there's considerable development of functionality, and out of that we've shown you a number of different applications, but you'll probably find more. And so if you're willing to share that, we're very keen to hear about it. We could have done more. We could have given you ability to manage distributions for traits and markers within each end use, but we didn't think that would add much functionality compared to what exists now in the software. Likewise, we could have given you ability to have separate committed matings lists for each population. And it's possible that is of value to some of you. You can let us know about that. As it is, we've extended functionality quite a bit. We hope it works for you and that you enjoy using the new multiple end uses. Thank you for listening.